The dynamo effect sustains the Earth's magnetic field thanks to convective motions inside the Earth's liquid core. The convection, an inherently turbulent phenomenon, might however be interacting with a much more quiescent layer. Due to its thermodynamical properties and of the presence of light elements, the upper part of Earth's core might be stably stratified. Waves generated by the turbulent convective flow below can propagate within this stratified layer and affect its long-term dynamics. Signatures of this propagation can even be observed in the temporal evolution of the Earth's magnetic field. A similar phenomenon is observed inside stars like our Sun. It is also composed of a convective zone and of a stratified zone, whose oscillations allow us to probe its interior like a scanner. Closer to us, a similar process can be observed in our atmosphere, made of several layers, including the troposphere, in which we live and where most of the meteorological events occur, and the stable stratosphere above it. The shape and evolution of some clouds clearly emphasize the interface between these two layers, which is called the tropopause. We have built an experimental setup aiming at reproducing this complex two-layer dynamics in the laboratory. To achieve this, we use an unusual property of water, which reaches its maximum density at 4 degrees Celsius. By imposing a temperature difference across the tank, we obtain an unstable layer between 0 and 4 degrees, while the fluid is stably stratified above 4 degrees. Thanks to a high-resolution camera, we track the displacement of fluorescent traces in water, showing the two types of flow emerging in this system. The convective and turbulent lower layer induces waves propagating in the upper stable layer. In addition to laboratory experiments, we also perform numerical simulations, varying the stiffness of the interface between the two layers and the intensity of the convection or stratification. Experiments and simulations run hand in hand. Even if simulations allow us to focus on different parameter regimes, they are, for now, limited to 2 dimensions or to 3 dimensions over short timescales. Our results improve our understanding of the dynamics of the Earth's core and atmosphere, and even stellar interiors. The impact of rotation or magnetic fields, along with the mechanism responsible for wave generation, are currently being studied. Our results also pave the way for a better understanding of a surprising meteorological phenomenon, the quasi-biennial oscillation. This emerges from the interaction of waves generated by convection. The modeling of this cyclic change in the direction of the equatorial winds in the stratosphere might indeed be improved thanks to our results. The relevance of such reversals for the Earth's core and its potential effect on the magnetic field is another avenue for our future research.